So Artemis 2 will stay exactly as we know it, no discussion. Artemis 3 will then dock with the two HLS providers, with one or both HLS providers in low Earth orbit.
So let's hope it doesn't turn out like a bad April Fool's joke. But yeah, even that is already ambitious, to be fair. The irony of the whole thing is that the SLS was actually supposed to be NASA's all-in-one solution. It was supposed to be. And the fact that now they want to install, or are installing, an upper stage from a competitor rocket, in this case the Vulcan or whatever, that's a bit like Mercedes putting a BMW engine in just to win the race.
What is stated in the OIG report is that there is no redundancy for this elevator. That means if the crew goes down and the elevator fails, then they can jump the 40 meters. Or they have to pull themselves up on a cable. The system is built redundantly with double and even triple backup, but still, something can always happen if the technology is fundamentally flawed, defective, or if something just doesn't fit with this technology. That's when the... Hello, and a very warm welcome to the 9th edition of the Mars Chronican podcast, my dear friends. A very warm welcome to this very special occasion again, because we've found each other again, so, Alessandro and I, and we've managed to record another podcast episode for you today with some thrillingly exciting topics. First of all, hello Alessandro, thank you for taking the time again today.
Not looking, but still found. Hey there, glad I can be part of it again. Very cool, I'm happy too, and sorry that you had to wait so long. A lot has happened in the past 4 weeks. I also got sick. Sylvan, I'm not sure if you heard. I really got hit hard with a cold. That's why I have to apologize in advance. It might happen that I cough from time to time, but I'll try my best to mute it.
But it's great that you're healthy again. I also caught something for a short time, but that's life, especially with a toddler in daycare. So we prepared some really exciting topics. We'll start like we did last time. I think that worked really well and was well received. We'll also go through the topics that I've basically found on X in the weeks since the last podcast. Or not all of them, but the most important and biggest news, especially the ones that interested me that I picked out. And Alessandro has finally a really, really, really exciting topic for you. Would you maybe like to give a little teaser about it?
We can certainly do that. I also want viewers and listeners to know what to expect. Do you know the Ad Astra rocket company? Probably not. I didn't know about them for a long time, and neither did Sylvan. But I actually came across it. They're doing something really cool with their Vasimar propulsion system, namely plasma drives. And what I think is great about the company, of course, not everything gets leaked, that's clear. But a large part of the technology, a large part is simply available online. And today, we're going to take a closer look at it in a deep dive. Let's break it down a bit and get to the bottom of what is actually meant by plasma drives here and what's happening with them. And we'll also take a detailed look at a few other small, exciting things.
I love technical papers as long as I don't have to read them myself, but when they're explained to me and I can just relax.
Just lean back, exactly.
Can lean back. But technical papers, when I have to read them myself, I also enjoy it, but less than when someone explains it to me. I'm more of an auditory learner. Exactly.
It can get exhausting quickly, that's true.
So,
good.
Then I would say, let's start. No, not would say. I'm definitely saying that we're going to start right now with the very first topic of our news lineup, and that's Blue Origin. They're incredible. They're putting things out now. It's unbelievable. One big, gigantic announcement after another. I mean, they've now posted their engines for the next New Glenn first stage here, which is already pretty intense for Blue Origin, considering what we're used to from them. But that's not the only news they've dropped here in the last 3 weeks. That's already very open by Blue Origin standards. You can see 7B4 engines here, which use methane and oxygen, and that should be in Kent, Washington, if I'm not mistaken, where they manufacture their engines. Maybe I'm wrong about that, whatever. So that's that. Anyway, here you see 7 engines that are standing ready.
Anyway, have I already outed myself as an absolute Blue Origin fan? I'm not even sure.
No, but I'm also becoming more and more of a Blue Origin fan, so it's definitely justified.
Yeah, I agree. Blue Origin was under the radar for a long time. We've mentioned that before. But by now, what the guys and girls are putting out there is really impressive.
Exactly, I think so too. There. Blue Origin, Isar Aerospace here on the screen. Tomorrow is the day. Tomorrow, they will make their second attempt to bring their rocket into orbit. How high do you actually estimate their chances of reaching orbit tomorrow?
Well, if you asked me like that, I would, of course, say 50-50. Because either they'll make it or they won't. No, but yeah, good question. It really depends on many factors, and it's only fair to say that as we've learned over the last, well, you could almost say decades, but especially in recent years, it's been relatively difficult to gain a foothold in the space industry or in the space business in general. You just have to say that. But yes, Isar Aerospace is just doing a lot of things right. Just the fact that if we say, okay, hey, this company was actually founded as part of a student project at some point, that's a bit of an exaggeration. When was that? Yeah, about 10 years ago, give or take. I think 2016 or 2018 was the official founding year. And for being so young and already having integrated so much vertically, it's impressive. Impressive. I have to say there's really a lot happening. The upcoming mission will also be quite exciting. So the ELSA M, I think that's mentioned in this post as well, right? Is it included there? I can't see it clearly. Yes, it is. Yes, ELSA M, interesting thing, end-of-life services by Astroscale Multi. You can actually imagine it like this. I have a funny analogy because I was talking to a colleague about it recently. Imagine you had to cook in a dark kitchen. Right, with 1,000 sharp knives flying around uncontrollably. That's super abstract. Yeah, whatever. That's roughly the situation in Earth's orbit because of space debris. And they're flying a mission here with Astroscale. And Astroscale is providing the tow truck, so a spacecraft that theoretically uses magnetic plates or robotic arms to capture old, inactive satellites. That's the idea, at least. The goal is actually clear here as well. The aim is to somehow guide the space debris or all these pieces of junk in a controlled way into Earth's atmosphere, where they will eventually burn up. Yeah. By the way, that's also called active debris removal, or ADR, if you ever come across that term. But to get back to your question, how likely is it that they make it up there? They will definitely pull off a liftoff, guaranteed. And I do think it's a remarkable sign that they have something on board, that it also has some significance. I'd rank it fairly high, but won't give a specific number.
Yes. Yes, I don't want to commit to a number now either, but maybe I'm also a bit biased and I wish for it. That's why I would just tell you over 50% chance of success, but I can't prove it. I have no evidence for it. It's just a gut feeling. So don't hold me to it and don't judge me for my assessment here. So, exactly. Then we've taken care of that. Next topic. Thank you very much. NASA is targeting the rollout in 2 days. Originally planned for the 16th after the last press conference of the Flight Readiness Review. However, it was apparently postponed by 2 days, and in 2 days, the rocket should already be rolling out to the launch pad. Und now they're talking again about maintaining the opportunity for an April 1st launch, but because of the time difference, for us, it will be April 2nd. So it will be 12:24 a.m. April 2nd for us. So don't let this April 1st confuse you. That always confuses me too, especially when these launch times cross into the next day and so on. But in this case, that's what it's about. So the launch window opens at 12:24 a.m. Central European time on the 2nd. April for the Artemis rocket, and even with a 2-day delay, also the same times. Crossing into the next day, but then there will be launch windows because we haven't heard anything from NASA yet. They said they need about a week and a half. Sorry, I'll be right back. They absolutely need a week and a half at the pad, more like 2 weeks. The launch window opens for Central Europe. Und nicht
Und
trudeln
selbst das
müssen,
ist
wie
schon
man so schön
sportlich,
sagt.
ne? So let's hope it doesn't turn out like a bad April Fool's joke. But yeah, even that is already ambitious, to be fair. So yeah, I don't know either. Artemis 2, I'm a huge fan. Of course, I'm totally on board with Artemis 2 because I'm also working on Artemis 2 more or less. But if you still look at it with a new Glenn, a Starship, and whatever else, then of course you can legitimately ask the question, how sustainable is the whole thing? Designed because somehow it already seems like it's kind of a mix of things. So at least they basically stole the solid rocket boosters from the space shuttle and then just stuck the whole thing onto a modified Saturn V. So it's always a bit tricky. But anyway, let's just wait and see what happens. As you mentioned, NASA is preparing for humanity's return to the moon, so things are getting serious. Step by step. And I think you also made a video recently about why it's actually a good thing, or rather what's going on with the Artemis missions. There was some disagreements, which was interesting. I still highly recommend it. Yeah, let's see what happens.
Yeah, absolutely. So apart from this whole Artemis 2 thing, there was also a huge update on the entire Artemis architecture. We'll get to that later. I also made a separate video about it. You'll find both the mission briefing for Artemis 2 linked below, as well as the changes to the Artemis architecture, although nothing is happening with Artemis 2 in that regard. There's no more tinkering with it. It's already at such an advanced stage that it just makes sense. No more tinkering has been done without somehow to show, I would say. Exactly. Artemis 3, 4, 5, 6, and so on. Those will be a bit different. We'll get back to that briefly later. As I said, if you want to watch a produced video, just check it out after the podcast because it's linked below. So, next topic. The space engineer posted this video earlier. I haven't had the chance to really analyze it yet. He found something during the startup of Raptor 3. Something is coming out there, and that's apparently not so good. But I haven't had time to look into it, so let's leave it for now. That's also very interesting. Eric Berger, for those who don't know him, is kind of the go-to source for space news. He's been doing this for decades.
He was one of the first.
He's the best connected of all, I'd say. He really, really has good contacts. On one hand, he has good contacts and therefore a good sense for things, but he also gets a lot of insider information. Not from a stockbroker's perspective, but simply from a news reporter's point of view. He gets a lot of insider information and, as I said, also has a very good sense for things. He apparently sent a request to Blue Origin, asking if Blue Origin gives their employees stock options. And funnily enough, just by coincidence, a few days later, he didn't get a response. A few days later, yeah, that's a good one. Limp, the CEO of Blue Origin, sends a message out to the staff. Hey guys, we're now announcing a stock option program for our employees, which is really cool and also shows that they've become more dynamic and not rigid or not stubbornly sticking to some rigid structure, but rather an idea comes in and within a week it's implemented. We didn't see that from Blue Origin 2 or 3 years ago. It used to be this sluggish giant that slowly moved through these waters, and now it feels much more agile. A lot more things are happening now. They post a lot more, they let us see a lot more, they give us a lot more insights.
A lot more participation. So Blue Origin has really changed for the better, considering that it has also become a kind of conglomerate in the space sector, like a huge company. I mean, if we compare that now with an Airbus, with a Leonardo, God forbid, a Thales, those are all such huge, huge companies. I mean, the merger is still coming up too. So if you merge 3 huge companies, you end up with an unbelievably, ultimately massive company. Whether that will really, how should I put it? Whether it makes sense, well, that's written in the stars. That's for others to judge. Above my pay grade, above our pay grade, I would say. But yeah, size doesn't equal speed. That's something you should always keep in mind. And I also think it's cool, like you said, that they're so agile that they reacted to it and said, hey, we're offering something to our employees. And by the way, that's also a very, very important point for space travel itself, because to put it simply, in what you might call the hard sciences, right? You don't just win with the best physics in that sense, but also with the best minds. It's all connected somehow, okay? But if the engineers feel like their rewards are just, let's say, play money, which actually happens quite often, then they just leave. And Blue Origin is also, of course, under enormous pressure here to finally get the New Glenn flying, to really get it flying properly. I mean, the thing has already lifted off, but we'd like to see more, right? Of course, we also need, or rather Blue Origin needs, a motivated team that sees some results not just in the stars, but also in the bank account. So fair enough, good work should be well rewarded. I'm the biggest fan of that. It would be nice if we could see that more often across different industries, of course.
Yeah, there are stories from old SpaceX or even newer SpaceX employees who, to put it bluntly, made an absolute fortune, because they simply got stock options that just exploded in value. And then you work for a few years at a company, get your stock options, sell some shares, and you've really made good money. Especially the really, really early employees. Some of them are actual millionaires.
Yeah, of course, if they got ESOP options, that's awesome. By the way, I just have to get this off my chest right now. Hey, I'm telling you, from my personal circle, from private circles, I know the following, or rather, many of you who might not work in the technical field but are interested in it probably know this too. I'll just say maybe in marketing, in HR, whatever it may be. And I just think it's a real shame that many companies, really a lot of companies, it doesn't matter at all whether we're talking about rockets, satellite constellations, drone manufacturers, big or small, hyped or not hyped, that the technical staff there sometimes, not always, but sometimes earn significantly above average compared to, I don't know, a really good HR manager. This is equally important since these are the people who find the right talent for the company. Without them, it wouldn't work. And I think, or actually, I don't just think it, I know it from, let's just say, I just know it doesn't matter from where things are going better at Blue Origin. So if you ever get the chance to start at Blue Origin because you have a green card, go for it. Just do it, please. And even if you apply for HR or something else, you'll be much better off than if you applied for HR at Company X, a German company. That's just how it is. It's a fact. And I think that's something we need to learn from, unfortunately.
Yeah, especially the US. I think they approach this talent thing a bit differently than Europe, because somehow I feel like here in Europe, we just train people. We actually have some really, really good training programs. And then what happens with the talent is, well, what do we do with them? There aren't really any programs to actually keep them here.
At least that's how it feels.
They fight over these people, they pay them, they throw money and gold at them and try to keep them and really bring them into these companies and give them opportunities, give them prospects, which unfortunately are still far too rare here, but it's getting better. To be completely honest, you also have to say it will get better. But one thing before we move on to the next topic, Blue Origin, because you mentioned a conglomerate, they are building a partially reusable rocket. They are building a Mars telecommunications network. They want to build a Mars internet network. They want to set up moon communication. They are building moon landers, space stations, so many different systems that they are working on in parallel right now. And that's infrastructure, molten regolith, and something else, zero boil-off technologies. So
there are still real technologies
that will be incredibly valuable in the coming years. And that was maybe one of the things they did while they were keeping a lower profile. They simply did research. In the end, it was simply a research company. And now we have...
I'm realizing again what R&D is like. That just shows you how important research and development really is. And that's also one of those things in the research environment in Germany. Well, it's just a shame because sometimes it's actually like that. Even as a small company, you're obviously dependent on funding. That's just how it is. And that's how it should be. Research should be paid for. That's obvious. Research that isn't funded just won't work in the kind of system we live in, and that's fine. But if you're a company that kind of pushes back because you're not 100% funded, but only, I don't know, 50, 70, 75%, then they say we can't do that or we'll be deep in the red. Yeah, but with the strategic outlook you might have in 10, 20, 30 years, you might have made that back 10, 20, 30 times over. It's always an issue. We Germans especially, and I think it's similar in Austria, but in Germany it's really bad. We really need to step out of our comfort zone and become at least a little bit more willing to take risks. Just a little, only a little.
After all, we're talking about a country, the only country in the world where you can drive without speed limits on the highway, at least in some parts.
Yeah, that's true.
You couldn't imagine people more willing to take risks. But that impression couldn't be more misleading. That's how it is. People like to take risks when driving, but in all other areas or in many other areas, they'd rather not.
Yeah, true. Good analogy.
That's kind of interesting. So, next topic. This is basically the article about what we just discussed. Yes, SpaceX. We talked about that briefly last time. SpaceX has submitted an application to the FCC, the Federal Communication Commission, to send 1 million satellites into space for orbital data centers. And as is common in the US, when your competitor announces a big move, the first thing that happens is a lawsuit, just to calm things down a bit. So that no one overreaches, so that no one thinks they can just do whatever they want. So Blue Origin just filed a lawsuit and says that it would take centuries to get 1 million satellites up and running. And even if all global capacities were used for this, it would take decades. And that would be impractical, unfeasible, and is more of a lofty ambition than a real plan.
I can also understand Amazon. Absolutely. I have to be honest, from their perspective, because Amazon is building, just from Amazon's point of view, they're building Project Kuiper, their own satellite internet. And in space, there is only a limited amount of room in orbit. That's just the way it is, even though it's obviously huge. But still, we have limited space. Just in terms of licenses, of bandwidths that are being transmitted, whatever it may be, it's definitely limited. If SpaceX, from their perspective as a competitor, reserves a placeholder for 1 million satellites, then they're basically blocking the competition. So from a strategic point of view, I can definitely understand Amazon to some extent.
Yes, absolutely. I think so. And I don't think it's seen that way there either, like someone is offended or something. No, not at all. That's also part of the business, just like that's simply a completely normal part of this business. I think everyone at SpaceX expected that either ULA or Blue Origin or someone else, some other satellite operator, someone would file a lawsuit. And I'm almost certain that they probably already reserved a small part of their mental bandwidth for this part of the project during the project development phase.
Exactly.
This is not the first time. SpaceX has already sued NASA. Blue Origin has already sued NASA. They've already sued governments.
That's just what you do in daily business. Just sue everything that's in your way.
Completely normal. And with these amounts, for us, it would be unthinkable to spend, say, 12 million or so on some lawsuit where it's not even certain what the outcome will be.
As a private person, you might wonder if you can file for bankruptcy, which is common now, even just driving 100 kilometers. But it's different for companies. Sorry. That's another thing. That's true too.
Exactly. Yeah, so much for that. I think that was already quite exciting. A few nice shots of Starship S-39. Ship 39 was cryoproofed, which means it was filled with cryogenic substances without engines. I'm deliberately not saying fuel because I think at first they only filled it with nitrogen and later on they filled it with methane and oxygen, and there are some beautiful shots. And I have the feeling that these starships look fuller when they're completely filled up. I'm not sure if that's just an impression.
You still know. Why? Warum Starlab? Wie meinst du das?
I just didn't measure it, but it all looks a bit fuller.
Then it's just an optical illusion. Otherwise, that would be disastrous, especially for the aerodynamics.
Yeah, so it's just to make it look more impressive. But what I saw, unfortunately, I didn't mark it. Someone took a close-up of the SLS rocket during the wet dress rehearsal, like a screenshot from before and during the wet dress rehearsal. And you can see how the rocket as a whole got smaller. Crazy, because all these cryogenic fuels, this material just contracts so much that the rocket actually loses about 0.5 meters in height. At Blue Origin, Jeff Bezos said they lose almost a whole meter in height just by fueling the thing with cryogenic propellants.
Likely with New Glenn, right? With its size, that makes sense. Yeah, that's true. With space, I mean, with SpaceX, with Starship, I'd actually be a bit surprised by that because stainless steel is actually relatively stable when it comes to cryogenics. Stainless steel is known for being able to withstand both super cold and super hot environments without the material density or anything like that changing much. Sure, I mean, yeah, a fully fueled complete Starship with a booster, maybe there would be some changes, but not to the extent of something like a New Glenn or the SLS. That would actually surprise me, but I don't have an answer for that right now. It would be interesting. It would.
Yeah, what fascinates me most about that is that, for example, with the New Glenn, everything still works anyway. Because all the lines have to grow in exactly the same proportion. Or it has to be built in such a way that if it doesn't grow in the same proportion, it doesn't break or get damaged or fall off or something like that. So it's insanely fascinating to think the whole thing through, to calculate it.
Absolutely.
Hats off to those people who are capable of that.
That's actually a great topic, especially if you don't go into computational fluid dynamics and just generally think about what else you need to consider. So with a rocket, it's not just about building a propulsion system, having 1, 2, 3, 4, 5 stages and then launching. There are all these little details you absolutely have to think about. So really cool topic.
Exactly. So we've taken care of that. A solicitation from the US government or from NASA for a Vulcan Centaur V upper stage for the Space Launch System. That means the moon rocket needs a new upper stage, as NASA has decided. So it's also pretty much certain that the second upper stage, the exploration upper stage, which in my opinion was extremely problematic, is not cancelled, not scrapped, not called off. And now NASA is looking for another upper stage or wants to upgrade the ICPS and has now announced that they are looking for a company to manufacture this upper stage because they don't want to award another single source contract to ULA again, because that's the mess we're in. ULA somehow got 500 million for the ICPS, for the development, and is paying for an upper stage that was used because it already existed. So there was no development or very little development work.
You learn from your mistakes, it seems.
You learn from your mistakes in this case, yeah, really. And then they somehow demand another 500 million for each ICPS they provide. And by the way, the exploration upper stage was also another $1 billion project where each upper stage also costs several hundred million more. So it's completely absurd, the kind of prices that are being thrown around there. And that's why Gerald Isaacman said, hey guys, he probably didn't say it in that tone, but if I had said it, I would have said, are you crazy? Not with us anymore. Because the way I see it, that's just a ripoff of the taxpayer. That's just really I can't imagine how an upper stage like that can cost so much.
And the irony of it all is that SLS was actually supposed to be an all-in-one solution for NASA. It was supposed to be. And the fact that now they want to install or are installing an upper stage from a competitor rocket, in this case, the Vulcan or whatever, that's a bit like Mercedes putting a BMW engine in just to win the race. So it's a bit strange somehow, but well, you have to support and help each other somewhere. But as you already said, the ICPS, which stands for Interim Cryogenic Propulsion Stage, it's solid, but for really heavy loads like going to Mars or let's say anything heading toward outer space, it's a bit underpowered, you could say. And the Centaur 5 is like a highly efficient sports car engine for space because it uses liquid hydrogen, that would be LH2, and liquid oxygen, so the classic LOX, which provides the highest specific impulse, meaning efficiency in that sense. Yeah, it's a bit weird, but hey, the main thing is that things are moving forward, right?
Yeah, absolutely. I think it's incredibly awesome what Jared Isaacman has set in motion here. He made sure that NASA not only didn't get any budget cuts, but actually got more budget. That Artemis is being restructured, made more efficient, and that the components that are pointless or absurd are at least being eliminated. If you already say, okay, we're doubling down on this rocket that we have now, that we have to use now, because there are no other options available, that at least it's set up in such a way that, I don't know, you save another $1 billion per launch or something like that.
Yeah.
But I
have to honestly say, Jared was for me, and I think for us, I'll speak for both of us, absolutely the right choice. So Jared Isaacman really deserved it, to be fair. He's worked his butt off his whole life, and you can really see that entrepreneurial mindset in him. And that's just awesome. I really think it's great when you actually manage to steer such a huge organization in the right direction. I mean, Artemis, we've changed a few things fundamentally, and now this whole thing with the solicitation, it's just not that easy, because even if you're the administrator of something like this, it doesn't mean you have everything under control and can do whatever you want. So that's impressive to me.
Yeah, so he brings the entrepreneurial knowledge and talent. He has this diplomatic sensitivity, but he's not a career politician. That he's only good at diplomacy, but he's also enough of a businessman to say at the right moment, okay, guys, with all due respect, but not like this. This is the limit and no further. Yeah, but now let's do it with common sense. Because a lot of what happened just happened based on some favors and some abstract definitions, where he just drew the line now. And that's not easy. Balancing between industry, politicians, senators, trying to satisfy everyone without offending anyone, and getting all the employees on board at NASA. So it's an incredibly, incredibly narrow path and quite a balancing act that he managed there. Well, in any case, gladly. Yes, that's the announcement again. That's the explanation, which can be translated like this. Exactly, but that's the explanation from NASA again, why for this whole thing we've just discussed. This explanation provides the justification for the fact that the contract was not awarded through a full and open competition. And United Launch Alliance received a sole source contract to procure replacement upper stages for use in the space launch system for the Artemis 4 and the 8 missions. They simply said, you're getting this mission, these contracts now. How much do you need here? Yeah, 500 million each. Okay, that's fine here. That's pretty much how it went. And now there's just an honest tender, and the best one simply gets the contract, just like it should be.
Yeah, if that's really how it goes, of course, we don't really know what happens behind closed doors or whatever. That's obvious. But yeah, it's definitely a step in the right direction. Definitely.
Exactly right. Moving on.
By the way, at this point, props to the ESA. I have to say that here. Props to the ESA. They actually do a really good job when it comes to tenders. The ESA also has such a huge budget, and the budget is divided into various departments. Now, regardless of whether you have a topic that might fit into several departments, and they really do a good job, when it comes to evaluation, they're really fair, at least from what I've seen so far.
Yes, that's true. Except so far from what I've seen with I mean, to be fair, there weren't many options either. But when it came to the production of the launch vehicles, it was more like the tender was tailored to the Vega and the Ariane. But yeah.
There weren't many options. Yeah, that's true.
So Starlab by Airbus, designed by an Austrian architecture firm. Based on the A-loop habitat Airbus, and I think that's with nanoracks and Star. Something else. Are they in on it together? Wait a minute. Who was that again? Starlab is being made by Airbus, right? And they're supposed to be on the station has a diameter of over 8 meters, and they're supposed to launch on a Starship rocket. And if I'm not mistaken, they recently officially booked a mission on Starship for $90 million US. But unfortunately, I didn't save that here.
Starlab. I think the others are called, is it Voyager Space?
Voyager, exactly.
Right? Could be.
It's pretty, I mean, there is also Voyager that has
I'm 99% sure.
Yeah, I think it's Voyager. Wait, the logo will probably show up at the end. No logos. Damn, but I think it was actually, I wanted to, but they also have one,
It's always pretty certain that it's Voyagers.
And I think Rex is also involved there, if I'm not mistaken. But since I think they'll probably start next year at the earliest. But I think they've made some design progress now and have shared a few things. I just wanted to quickly share that with you. Here you go.
By the way, super interesting about Starlab, because you could say it's like I'll call it a flying biolab, because it would have. So Starlab really wants to focus on biomedicine. It's really exciting because by now we also know that in zero gravity, cells and fluids behave differently there than they do on Earth. It makes sense with microgravity, of course. And there are two interesting points about that. First, there's 3D cell growth, and second, the topic of crystallization. If we look at 3D cell growth now, so without gravity, cells grow in all directions, not just in one direction. And you can basically grow real organs or real organ models instead of just flat cell layers in a petri dish. That's one thing when it comes to cell growth. And with crystallization, it's also interesting because medications can often crystallize much more purely in space, which also massively accelerates research, for example, on active ingredients against Alzheimer's, cancer types, and peptides in general. So it's really fascinating.
Yes. Biomedicine will be one of the biggest driving factors for industry in low Earth orbit.
Definitely.
I think there's a lot of potential. One of the biggest things that always comes to my mind are these bio 3D printers. They work with your own DNA material and use nutrient solutions to basically create patches from your own DNA material. So you have a patch made from your own skin, so to speak. It's totally crazy.
But super exciting. And of course, we shouldn't forget that the ISS is also slowly heading towards retirement. And that's obviously putting pressure on things as well. Right. So it's basically an attempt to transform Earth orbit from being a government outpost, which is what the ISS ultimately is. Turning it into a commercially used lab, maybe a district or so, might not be such a bad idea.
Yeah, a Starlab, if I'm not mistaken, has about 270 or 300 cubic meters of space, if I remember correctly. It has roughly more than that.
I think it was 400, because you also have, well, it has a diameter of 8 meters, or at least I think it's supposed to have that.
8 and 8 meters high, approximately, in total.
But with spheres, you get to 100, and that's a lot. So if you look at the modules of the ISS, they're about 4 meters wide. So that's quite something. A larger volume, of course, also allows for more research capacity.
Well, what I remembered back then is that Just 3 of those modules already offer more space than the ISS, and that's really impressive. Actually, definitely involved like that. How many does it consist of?
I can't really say. I actually don't know.
There are a lot of modules.
Are there more than 10? I'm not sure now.
I have in total, with the smaller modules, how many modules are there? Should I just shamelessly Google it now?
In the background was...
Yeah, we can do that once. We can't know everything, so don't be mad at us. How many modules? That probably depends on whether you count the radiators and solar panels as separate modules.
Oh, great. Now I'm getting the individual parts spit out. Perfect, perfect. But still interesting, though. The ISS consists of a variety of components, including about 16 pressurized main modules, so 16 main modules for living and research purposes, and numerous trusses, structural elements, and solar panels. And that brings us to the number 40, but that's already quite a lot.
So that's basically a module. It does have a service module, the Starlab, if I'm not mistaken, but still, that's it. That gets launched in one piece and is more or less ready for operation, which is very interesting, by the way. The Congress has now commissioned NASA to find 2 operators for private space stations. And Starlab is one of the candidates being considered as a successor to the ISS. And that happened a week ago. And then the Congress, I believe, made the decision, or rather, NASA was urged to consider options to decommission the ISS not in 2030, but in 2032. So another 2 years of extended service for the ISS. However, I think it's not a done deal yet, but just under discussion for now.
Yeah, I could even imagine that it might get postponed a bit more in the next few years. At least I know for sure it'll be delayed by another half a year or so. That's always how it goes. But yeah.
Yeah, now they have this Dragon that can boost the ISS again, which means they now have this capability in-house. So it could very well be that they'll just keep adding time in 6-month blocks for as long as they need, you know. Now we have this massive architecture change, which is really cool. By the way, that's the reason for the whole thing. Mercury, Gemini, Apollo, Space Shuttle, Artemis, and SLS. In the end, up until the Space Shuttle, we had an average time between launches of less than 3 months. For Mercury, it was 2.5 months. For Gemini, 2.5 months. Apollo was 5.1 months. That's 5 months and 3 days or so. Completely absurd. And for the Space Shuttle, it was 2.7 months. And for the SLS, we're at 3.5 years. Completely absurd. And that's why Jared Isaacman just said, guys, we can't build up cadence like this. We can't build up routine like this. We can't push down prices like this. That's how we end up with Super. We just keep individual works of art here, each one costing a fortune every time and requiring an incredible amount of time every time. And every piece is a one of a kind. That can't be. Standardize it like this. Artemis 2 will stay exactly as we know it. No discussion. Artemis 3 will then be with the 2 HLS providers, with one or both HLS providers, and those in the niedrigen Erdorbit docken, validate all systems. That means the pressure on SpaceX and Blue Origin eases a bit, just a bit, but only because they're now doing this mission in 2027 instead of 2028, but without refueling and without landing on the moon. But at least the docking of these systems will be properly tested in low Earth orbit. And Artemis 4, 5, 6 and the ones that follow will actually be moon landings. And this renewed architecture envisions that if everything really goes according to plan and the cadence drops to under 10 months, then it would even be possible for us to see not 1, but 2 crewed moon landings in 2028 with HLS Starship and HLS Blue Moon. How realistic that is remains to be seen, but the ambition has grown and I like that.
Absolutely. And that also makes total sense because before it was more like a single taxi that was sent up each time. And now it's moving more towards fleet logistics. And I think that's maybe the most important point for the viewer or listener, what's happening here tactically. The SLS, of course, still brings people to lunar orbit with the Orion capsules, of course. But the big point is they also wanted to use it to bring up heavy cargo, fuel depots, and so on. And all this heavy cargo, fuel depots, the actual lunar landers like Starship, HLS, or whatever, those will, of course, be launched separately by private rockets. And that's kind of like driving a sports car to, I don't know, the airport, but sending your luggage ahead separately in a truck. I know that's not really the best example, but I think it's clear what's happening there, more or less. And a big point about this architecture, and that's kind of the biggest advantage I see there, because the Lunar Gateway system, there was always this question, is it really coming? What's happening here? Should we really keep pursuing this? There were budget cuts a few years ago with Trump and this and that. But the gateway becomes even more important here, because if we want to commute up there, we also need a rest stop, like a highway rest area. And of course, the topic of reusability is very important again, because landers can commute between the lunar surface and orbit, and therefore don't have to launch from Earth every time. That's only if we have a gateway in place. And about the topic of fuel depots, basically you park a gas station in space or something like that. And that also solves the fundamental problem of the rocket equation again. So you no longer have to carry all the fuel for the return trip from Earth. That's a huge point. If we consider that gravity on the moon is about 1/6 of that on Earth, that's just, so escape velocity from Earth is 11.2 kilometers per second, of course. That's quite a lot. On the moon, it's, I think, 2.4 or 2.35, 3.8, something like that. That's pretty much about a sixth, a fifth, somewhere in that range. It's not completely linear, but nevertheless, that's a huge advantage. And I hope that maybe the gateway will give another push in the next few months. Maybe there will be some more news, some more updates, some more announcements, so that things move forward again and something happens back and forth. But yeah, let's just wait and see.
I know I'm not a big fan of the Gateway project, because I think you could just use a Starship that's parked in lunar orbit as a rest stop. Because you dock the huge Starship with about 600, 700, 800 cubic meters of usable space, or let's just say 500 cubic meters of usable space to the Gateway station, which maybe offers 150, 200 cubic meters of space. Yeah, the usefulness, maybe I don't understand everything, but Jerry Isaac, man.
That, and also that's actually a really good point. We can touch on that briefly. You have a few issues if you only had one Starship in orbit, so to speak. First of all, I would say this is a topic of fuel management, or let's call it a refrigerator, because Starship mainly uses methane and liquid oxygen. And these substances have to be kept extremely cold, really cryogenic. Starship is big, yes, but it's not really built for that, at least as far as we know. For example, to park passively in sunlight for months or even years, or to be in a strange lunar orbit without the fuel slowly evaporating, for example, so that we don't see a boil-off effect, for example. In deep space or outer space, which now of course includes the moon and its surroundings, you have completely different conditions than in Earth orbit, just in terms of radiation exposure and microelectronics alone. And the gateway actually serves much more as a stable control or relay station, and is also designed, for example, to remain autonomous in orbit for over 15 years. And that's with massive solar arrays for power supply, for example, or rather with highly precise communication systems. You can't really install that in the Starship anymore. That just doesn't work at the moment. Of course, it's possible that SpaceX is already working on it and says, hey, dear NASA, your gateway will become redundant because look at what we've done here. We have something in Starship X point, whatever that's exactly designed for that, whatever it is. But there are a few points that a Starship just can't cover. That's just one topic, like fuel management. Then there's also the topic of the safe haven in terms of redundancy. So imagine, for example, with the Starship, there's a technical problem. Not sure, it could be a leak in the life support system. And all of this happens while the moon astronauts are in orbit. So a complete disaster. Without the gateway, they would need to try returning to Earth right away using the Orion capsule. But with the gateway, they have a safe haven. So in that sense, redundancy, there are supposed to be supplies, oxygen, living space, all the stuff you need up there. And another really important point is, and I'm almost done with my little space lecture, you have the gateway as, let's call it a station. As a German, I always use the word station, and yes, a station for different trains. Because on the one hand, it's supposed to be international and interoperable. So it basically has a docking adapter. You can imagine it like a USB-C adapter or something like that, but in the space sector, so to speak. Not just for SpaceX, but also for NASA capsules, in this case, Orion or something like that. It's designed for European service modules or for future countries and other companies. That's a big point, because if you only rely on Starship now, you're obviously also tied to its design. Gateway is more of an open platform where different nations and companies can dock their own modules, something like that. Yeah, that's all I have to say about that for now. That's why I'm a strong supporter of Gateway, honestly. I think it's cool in itself, especially in terms of building redundancy and creating a safe haven. You need something like that when you're way out there. But that doesn't mean you couldn't also park 1, 2, 3, or even 4 Starships in orbit as well. Maybe, of course, in a slightly different orbit, maybe for other use cases as well. Obviously, if we're just talking about fuel with Starship, we've already established that's a bit tricky. There are definitely other cool use cases that I can't even think of right now. But yeah, definitely a good point.
Yeah, that would probably even be a topic for its own podcast where we just chat about the Artemis architecture. Yeah, because so many things come to mind now, but I also think all your points are totally valid. And honestly, I've never really looked at it that way. I just know that Jared Isaacman isn't a particularly big fan of the Gateway project as part of Artemis, but he definitely wants to repurpose the modules that have already been produced, but not for Gateway or Artemis, but rather as platforms for research on nuclear propulsion in space. There certainly are.
There are definitely points that we've somehow completely overlooked or something. I'm pretty sure about that.
Yeah, so I'm not sure if I'm considering all the points here. So we still have quite a few points left, but we probably won't get through everything I planned here because we want to leave at least 20 or 25 minutes for your plasma thing. But I'll go through a few more points now, and you just let me know for sure. Let me know when you think, okay, from now on, we should definitely move on to yours. Sounds good?
Of course, we don't want to keep the viewers waiting too long, but as far as I'm concerned, if you still have some cool news, let's go through them as well. Where you think, okay, we need to mention those briefly, right? That's exciting. We should go over that. Because my plasma thing, that won't take too long. It'll be done in 15 to 20 minutes. Of course, we could drag it out endlessly, but we won't do that. Of course, we still need material for other episodes. So from that perspective,
there's no shortage of material.
Very good.
Here we have a plan from SpaceX, or rather of Starbase, where you can see, could it be that we already talked about this last time?
We saw aerial views of it, or rather a few aerial photos, exactly.
They're basically annexing this area. So currently, this yellow line you see here, that's Starbase, the SpaceX city. And what's marked in blue here is supposed to be annexed and become part of the city. What that means is that these areas will also receive city services. Starbase means police protection, fire department, infrastructure, water pipes, etc. It's also not unthinkable that SpaceX will really start doing that. It's actually very likely that these areas will actually be developed if they want them to be marked out here so explicitly.
And for those who really haven't noticed yet, it really is a city. I mean, it's truly a city of Starbase, Texas.
Exactly.
Just like your hometown, it's also an officially normal, well, maybe not that normal, but it is a city. So that's pretty crazy when you think about it. A few years ago, there was nothing there except a bit of desert, some land, and down south is the border with Mexico, maybe some other problems, just a bit.
Yeah, but just a sleepy little retirement town with houses and stuff like that. Definitely, that was it. There wasn't much more to it.
I mean, I think it's amazing what you can accomplish when you have the will. It's always impressive.
The thing with the Gulf of America, this renaming, I don't know if the USA has the authority to rename any world region or any Gulf. They had the authority to found a new city in their country, and that's what they did. There are even court rulings for that. It was also a long process. Everything is properly regulated. Booster 19 Starship has performed a static fire with 10 out of 33 engines on the new pad. So gigantic. But it was an abort, as you can see here.
It's always fascinating to see that thing. It's so awesome. Yeah, that's right. It was an abort, right?
Exactly. You can see up there. There are only 3 grid fins, but that's not because it's unfinished. It's just that the V3 design only includes 3 grid fins. Also, this whole launch platform here, it's basically already the next generation of hardware. And they're moving faster in the test program than any observers would have expected. So it's incredibly exciting. Let's just go through this quickly now, here once again from the perspective of NASA's space flight. That basin down there actually fills up pretty quickly. And these clouds of mist that are forming now. There are no brown or darker tones left because it's just all water that's evaporating and not dust being stirred up. Yeah. It has opened up here so many times. This is what it all looks like from the air. RGV aerial photography since day one, my OGs.
They really bring awesome content, right? I think that every single time, also in terms of documentation, really great. Yeah.
I mean, this already looks like something out of a cyberpunk movie or something, so intense. That's just a gigantic tower with these arms holding some kind of rocket. It's just so absurd. What's going on there?
Yeah. You can really see the scale again there. Down there, you have a little van or bus or whatever. Something is down there.
Yeah, that's totally absurd too. This dimensions. Starship. Right now, this booster, as I mentioned, has just 10 engines installed. And here we see one of these grid fins up close. Very interesting. One of these grid fins is different from the other two. If you look closely here, these openings are slightly slanted. That's the right word. These openings are just tilted outward, so to speak. Unfortunately, I don't know exactly what the purpose is in this case.
Can't say either, but it definitely has something to do with aerodynamics.
Definitely. But if I remember correctly, that's supposed to be the middle one of those 3 grid fins, the one that's basically facing upward when coming back into the Earth's atmosphere.
They look so tiny, right? It looks like it's just a little fin waving around there. But it's actually a huge thing, right? It's something like 4 by 6 meters or 4 by 4 meters or something like that. So it's a massive thing.
I think you could fit 4 people in each of those openings. They wouldn't have much space, but you could just put 4 people in each of those openings. It's a massive thing. Dozens of tons. And here we are again at Blue Origin. 2 years ago, we got pictures from the factory hall that were simply empty, brand new. All the tools were nicely arranged. No hardware to be seen. And now something's happening there. Look at that. Those are all first stages in different stages of completion. Hardware lying around. People on the move. I love that. I love that.
It's alive.
Absolutely, exactly. So super exciting. They're building up this cadence right now. This is all still in the flat phase of this exponential curve. This is, we can definitely expect something from Blue Origin. So here in speed mode, once again, Starbase Surfer also takes insanely cool photos, like that shot just now of the booster.
Insane, right?
Beautiful. It blows me away. Here, once again, here you can already see a bit of what this engine configuration looks like at the bottom. These engines, these Raptor 3 engines, have almost no shielding left, no cover, no protection anymore, because they are already so robust and everything has been internalized, if you can put it that way. Everything has been designed inward into this engine. Classic vertical.
Really cool job.
Yeah, really crazy. But it kind of looks like someone who lost a few teeth. But that's still to come. There are still 23 engines missing. And they fired the thing in that configuration. So here's a test with the grid fins. Take a look at this.
Actually pretty bold, right? When you look at it like that.
Yeah. Well, cool. Yeah, a couple of grid fin tests here recorded by NASA Spaceflight. Starbase Texas took this photo. So Starbase Texas is an official city. We've already talked about that. They have an X account. And they posted this photo on March 10th. That's just how it is. Back then, this city was just this row of houses. It wasn't a city. It was just a little place.
Actually, it felt like there were only 3 houses, right?
Yeah, exactly. And then they were bought up, and back there, that should be Brownsville.
Yeah, looks like it. Yeah, that's right.
Brownsville. And over here on the right is Port Isabel, or I think that should be the Port of Brownsville, or the entrance to the Port of Brownsville. Thank you very much. Grid fin tests again. You've already seen that. I want to show you that up close. These engines, you only see these. What are flanges? Flanschen in German, right? That too already.
Ja, Flanschen, letztendlich, genau.
Here under this black thing is a flange that's basically covered, and the actuators of the inner engines, they also got extra protection here. You see this one where it says 369, that's a protective cover, and here as well. But otherwise, the entire engine doesn't need any more protection. And every time I see the engine, I have to think about when Tory Bruno publicly believed that this engine wasn't fully assembled and embarrassed himself a bit, which was kind of funny. I'll add a... He thinks an engine isn't fully assembled, but it actually is fully assembled. But it's so advanced and high-tech that it just doesn't look like a normal rocket engine anymore. It looks like it's just not finished. Crazy. By the way, 3D printing.
Can your 3D printer do that too?
Exactly.
Shameless advertising at this point.
Almost. That would almost be it. But it's really incredible how far this technology has come. Fully 3D. Completely absurd. Here we also have GS2, which stands for ground system. No? This is the upper stage from New Glenn, which did a test firing. So 43 seconds. Here we have a test firing. This is the next upper stage, already tested. So it's kind of like a long duration test. So Blue Origin is really stepping on the gas here in this speed round. Awesome. I just can't get enough of that site.
But you just can't get tired of looking at it. It's just always awesome.
Poof. I'd love to just lie down in there.
I don't know.
Thank you very much. But those are the engines after they fired for, I think, what was it, 2.5, 3 seconds. That's what they look like after the first firing. Yes, here you can see it even better, how the engine doesn't need any protection here. But here at the flange, it does. And here, these two actuators that are attached have received extra protection so that they don't burn up during re-entry.
Yes, that makes sense. By the way, it looks like the NSF from NASA spaceflight. Let's move to the next one. Looks like that's just a part of the engine. I was just thinking, can that be right? No.
Yeah, they're making the engines for SpaceX now.
New business.
but he's actually from NASA spaceflight, and now he's become the spokesperson for SpaceX.
Yeah, there was something, right? I heard about that in passing. Yeah,
That happened once.
because I know the name.
Chris Gebhardt, exactly. He became a comms officer or something like that at SpaceX. Very cool. That's really cool. Here we have another engine picture. You see, I love these views of engines. Thank you very much. Here we have another very interesting thing. Artemis. Here we have 108. So NASA, or rather the Congress wants that NASA vehicles are manually controllable. And SpaceX has a different opinion about that, especially because they had that experience with the Dragon. And there they had the same discussion where they said Dragon is not made to be operated manually. Of course, there are basic manual controls. You can control all systems manually, but you don't have joysticks for active control like Starliner or other capsules. But it works. That's good.
That's a good thing, you have to admit. The biggest source of error is usually human error.
And a computer program doesn't have shaky hands, doesn't get nervous, doesn't have blackouts, can withstand G-forces endlessly, can
Get it.
The machine is at work before the boss, doesn't sweat at work.
Wow, that was a total waste of time.
Exactly. But NASA is still a bit old-fashioned and says, hey, but what if the system fails? We need some kind of backup. And that's now a huge discussion between SpaceX, NASA, and Congress. And if this continues like this, also the OIG report, this Office of Inspector General report, clearly indicates that Starship HLS will probably have almost no manual control capabilities either. Better to build in systems.
Failure redundancy before I say that any pilot can really make a big difference there.
I also can't imagine that manually controlling a Starship HLS would be easy or even possible if you...
Yeah, especially since that's a completely different kind of inertia. You can't really, well, okay, you could build a simulator for that. Yeah, sure, but, well, I don't know either, so it's difficult.
I also think that if you really think it through, then software should be better at it than humans. And another problem, the OIG report points out or puts its finger on the issue of elevators. You can see here this elevator that comes out of the HLS and lowers the crew down to the ground. Was aber the problem declared by the OIG report is that there is no redundancy for this elevator. That means if the crew is going down and the elevator fails, then they can jump the 40 meters, or they have to pull themselves up on a cable. I mean, the system is built redundantly. I think it's double and even triple redundant, but still something can always happen if the technology basically, if it's faulty, damaged, or something just isn't right with this technology, then it could very well happen that the crew simply ends up stranded next to their spacecraft on the moon, which is really, really bad. And that has to...
I have nothing more to say. I don't understand it.
But also for Blue Moon, there isn't even a concept yet for manual control or how the crew is actually supposed to get out. Those are still unresolved issues. And for Starship, the critical design review is scheduled for the end of the year. And by then, hopefully, this problem will have been properly explained. Exciting.
We definitely need to talk about it again when the critical design review is here. Absolutely.
Yes, definitely. I hope we'll get better renderings of the final design then too. For anyone who's interested, I'll of course link this OIG report below so you can check it out for yourselves. I have the report open here now, but we're not going to go into it. It's 50 pages of bureaucratic English. All right, we can close that. Here we have this Starlab station again. This is what it looks like from the outside, with an arm, payload racks on the outside, solar panels, service module here, and an 8-meter diameter. Done, just like that. We're almost done with my topics. We're actually making really good time. SpaceX has started their constellation's descent. At least the shell at 550 kilometers is being brought down to 480 kilometers. The reason for this is simply faster or lower latency, higher bandwidth, and a quote-unquote safer orbit. If something happens, the debris will clear out faster from these orbits than if they were at 500, 600, 700 kilometers.
Yeah, that really does make a difference. So a few kilometers in altitude can really save time, especially when deorbiting, especially when things get critical.
Exactly. So it can make a difference between a few weeks or then a year, 2 years, 3 years, or even longer. It really happens very quickly. So it gets very long, very fast, how long it takes for this debris to come back to Earth. If you're at 600, 700, 800 kilometers, it can suddenly take years or even decades, or if you go even higher. And there at these lower altitudes you are, as I said, it's better for the consumers. SpaceX then has to replace the satellites more often. The lifespan decreases because there's higher drag, more fuel consumption, and accordingly, they have to be replaced more often. But exactly. So let's move on to the next topic. I mentioned this once in the Artemis briefing video, but it has been updated again. The second one wasn't really an option. What we're seeing now is actually the date on the 1st, which is the second one for us. And here are the alternative days. And on the 30th, April would also be an option. So yes, it remains exciting. The rollout has definitely been postponed by 2 days. Whether this will actually affect the launch date, if it has the same impact, we would probably then be looking at April 3rd launch, which for us might, yes, then for us it would actually be the 4th as well.
That actually sounds realistic, that it will be something like that. Let's see what happens next.
Yeah, let's see what NASA says after they've rolled out the rocket and done the first tests. We'll see then. Thank you very much. I only opened that as a teaser for one of my upcoming videos. Optimus will be the von Neumann probe. The von Neumann probe is a machine that flies somewhere, mines materials, and replicates itself. That's a very simplified explanation. But we have almost all the components of this machine independently. Develop them more or less independently. We have the MRE reactor, which can basically process these materials. We have mining robots, we have humanoid robots, we have AI that is currently being developed. So when all these things come together, combined with extremely cheap launches, we have a von Neumann probe that might even be able to prepare entire cities for us. Before the first humans even set foot somewhere on extraterrestrial soil or something like that.
Science fiction can become reality so quickly. I keep thinking about it. You might even know von Neumann probes from one classic or another. It's even a topic sometimes in Star Wars. Really awesome. So I'm really curious about that. It's really like, sure, it all sounds nice and good, and this could become Optimus. But you shouldn't forget about the Chinese. They're doing a lot in robotics and also in AI. They're way ahead. So it remains super exciting. We can also pick this up in a future podcast or something, because that's going to be very interesting.
Yeah, talk a bit more in detail about robotics, especially about these humanoid robots, because that's really fascinating. Because the world is made for humans. You always need hands. It's made for a world with people who are on average 1.7, 1.8 meters tall, with 2 arms, 2 legs. And if you have highly specialized robots with really strange hands that can't grab things the way humans do, then they're just highly specialized. And they're highly dependent on infrastructure. But humanoid robots can solve the same problems as humans, or in theory, the same problems that humans can solve.
Yes, definitely. For example, something like the figure 01, it's interesting, by the way, you could take a look at it. So figure 1 or something like that, just Google it. That thing has 25, that already blows my mind, with 28 degrees of freedom in the hand. So just as many degrees of freedom as we have. So they can actually control everything with the hand, maybe not as fine and delicate as a human can, but basically in terms of degrees of freedom, it's possible. An absolute masterpiece of engineering. That's just how it is.
It's really, really, really intense what's happening right now. All of this will be in one video. Figure 2 will be included as well.
You'll be featured too. Nice. Very cool.
So here we have Blue Origin once again with a big, super cool announcement. They are working with JPL at Caltech on a project called NEO Hunter, which stands for Near Earth Object Hunter, basically a planetary defense mission. We had the DART mission, where that refrigerator-sized probe crashed into Didymos or Dimorphos. And their orbit, it's a 2-asteroid system, a double asteroid system. Their orbit was slightly deflected. And now we basically have...
It works, at least if I remember correctly.
Proof of concept. And now they're working here with Blue Origin and JPL to continue this project with a larger impactor. And let's see how far we can get with this planetary defense program. Of course, based on Blue Ring, these upper stages, payload, adapter from Blue Origin, which is incredibly capable. It can supply the payloads with power, thermal stuff, with everything that satellites basically need during sun transits. These Blue Ring payload adapters can provide. And that's basically the foundation for many of the technologies that Blue Origin is currently presenting.
That's really exciting, super cool.
Right. So 1, 2, 3, 4, 5, 10. And now the last point. I think that's a Japanese H3 standing on the pad. I believe that must be Tanegashima at the Space Launch Center in Japan. And that looks like they have used fairings. But if you look at the comments, I really wanted to show you this. Maybe some of you are thinking, oh, Japan already has reusable rockets and Europe still doesn't. But Japan doesn't have reusable rockets. They also don't reuse their fairings, but rather those are mock-ups that were used in tests. And yes, these aren't the real fairings you're seeing here. But I just wanted to show you that and troll a little bit so I could say something funny here and we could have a bit of fun too.
Just this once.
Very good. So that was actually my last tab, and that brings us to the homepage. And if you have nothing more to add on this topic, Alessandro, then I would like to ask you to give us an overview of your prepared plasma topic, please.
Yes, let's go. Go ahead and share. I actually already shared, but we're already there anyway. It's about which of course fits the channel, about the Ad Astra rocket, about the Ad Astra rocket company, a really fascinating thing. I picked out a technical paper about the drive, the Vasimar drive to be precise. That's pretty cool. You can read all about it. So if you want to find out more, go to adastrarocket.com, then take a look at VSIMR here. That's the engine. There are also technical papers here. I'll open them quickly. I'll open them. Just a moment. In any case, there's an overview coming up. So here we are. There's the overview, the papers. That's actually pretty cool. They really share a lot here, all in PDF format. If you scroll all the way down, it started in 2000. By the way, interesting thing. Ad Astra Rocket Company wasn't founded by just anyone, nor is it a spin-off from something big. Well, of course it's something big, but it comes from a former astronaut, namely Franklin Chang Diaz. I don't know exactly how to pronounce it. So pretty cool. He actually flew on some of the STS missions back then. But what I want to get at now is, We're going to go straight into the engine here. I've already opened it once and I'll share the correct tab and then we can actually see something here already. Now let's zoom in here so we can really see what it's about. It's about the recent progress of this VASIMR engine. So a very cool piece of technology. It was presented by MIT, or rather at MIT. What is this about? Well, for one, maybe we should talk about what VASIMR means, because of course it's another acronym, like everything in spaceflight. It's always some kind of acronym, which funnily enough always fits perfectly. It definitely stands for Variable Specific Impulse Magnetoplasma. So you already know, or you can already imagine which direction it's going. Sounds a bit like Star Trek, I think, personally, but it's actually become real physics. And what we can already see here is how this thing works, because instead of burning kerosene and oxygen, you use a gas here, namely argon, a noble gas. And you make a plasma out of it by stealing the electrons from it, that is from argon, and then you heat the whole thing up. That then becomes plasma. This plasma is heated to truly absurd temperatures with radio waves. It's actually similar to your microwave at lunchtime, just millions of times hotter. And that's generally the thing. Whenever it comes to plasma, it gets unbelievably hot. I mean, we're talking about really, really, really extreme temperatures, but we'll get into that a bit more later. Another important thing here is what happens then? Well, this superhot plasma is then expelled backward through magnetic fields. You can do that with plasma, which is pretty cool, like through an invisible nozzle. So what do we get? Of course, thrust. Makes sense? The problem in the past was it should be here somewhere, the VX200 prototype. So here we already have the VX200 SS listed. Is it listed there? I'm not really sure. Yes, it should be there. But that was definitely the problem, because the predecessor, the VX200, had great performance values. They were really good, but it was insane. It was even insanely efficient. We have a specific impulse of 4,900 seconds here. So roughly speaking, that's a fuel-saving class in space travel. So not even that extreme. So it's good, but yeah, it could be better. Here it is in the middle. Where are we? Thrust efficiency. It's right in the middle. We just have an issue with the runtime. It's just a pure sprinter. So it could only fire for 1 or 2 minutes. Why? Well, because otherwise he would have simply melted away, to be honest. There's just no proper cooling system. And now we're talking about the successor, the VX200 SS, coming up next. The SS stands for steady state, meaning continuous operation, and that's the real sensation in this paper. We'll go through that in a moment, because the engineers have given the drive a new power supply, or rather a PPU, and an active cooling system, and the result is impressive. They ran the thing in July 2021 for 88 hours straight at around 80 kilowatts. Was it exactly 80 kilowatts anyway? Something like that, around 80 kilowatts, without it burning itself out. The sprinter has become a marathon runner. That's cool. But what does that mean for us now? That's important for anyone working in a technical field. You can derive a technical or technological, that is a TRL, technology readiness level, from this. So a skill or readiness level, in this case 5, usually ranging from 0 to 9. 9 means you've already had in-orbit testing, in-flight testing. 0 is completely new territory, so to speak, not even researched yet. 5 is actually pretty good. That's the assessment here. We can also see at the bottom of the text that was just raised, once again about this TAL scale. It's always a bit different depending on whether you ask ESA or NASA. There are some differences, but it's basically the same. At NASA, a TAL still ranges from 1 to 9. TAL 1 is basically a sketch on a napkin, and 9 means really reliable in space. That's how it is at NASA. We're in the middle, which means the components work together in the relevant environment. So we have a vacuum chamber here on Earth, that's the relevant environment, and the components just work. That's ultimately the proof that the concept is not only good on paper, but also really works in the harsh reality. So it's really a cool thing. And if we move on a bit now and scroll right down, just a second, where was it? Here we are. I think I'll zoom out a bit again, because now it's getting a bit more serious. It's only 10 pages, but it gives us some insight into what's happening. We have a few more here. We'll address them soon. What's interesting for us right now is this drawing here in the middle and a bit of what's written around it. Pretty ingenious piece, but let's just take a look at it. This diagram here in the middle, this figure 1, is really the heart of the whole thing. That's ultimately the VASIMR drive. So basically consisting of 3 decoupled chambers that function somewhat like an assembly line. Let's take a look at the 3 stages. These are basically always the classic 3 stages when it comes to plasma. First, we have the ionizer. So that's basically the plasma kitchen where everything comes out. All the way to the left, that's where the, let's call it normal cold gas comes in. So the propellant, that's this green, light green box here, basically. Here it's then shocked with radio waves, so to speak, until the atoms completely lose their electrons. And from a harmless gas, meaning the argon, it basically becomes a soup of charged particles. That's what plasma is. And this plasma is electrically conductive, but still relatively cool. That's why we need a booster. That's this RF power box, the yellow one on top. I'll zoom in a bit here again. You can see it a bit better that way. So you can see it quite well like this, I think, right? Yes, exactly. Exactly. This is, so to speak, the microwave that was briefly mentioned earlier. It gets pretty wild there too, because the plasma flows into the middle chamber. And here, really massive amounts of radio frequencies are blasted in. And it's exactly at the resonance frequency of the ions. So I call this ion cyclotron heating. You can imagine it like this. It's as if you're pushing a child on a swing at exactly the right moment, at the perfect moment. So the particles build up to really absurd temperatures. And we know that the more and the stronger the movement is, the higher the energy. And the higher the energy, the higher the temperature. An increase in temperature means particles move faster. That's why this analogy with the swing. And what's also very important, we have a third stage, which is the magnetic nozzle. And I would say it's like an invisible exhaust because you can't really see it here. The plasma is way too hot for any known material. So we also have this problem with, well, plasma in the classic sense, for example, with stellarators or in nuclear fusion in general. It's so hot, it would actually melt away any material instantly. No? But like, for example, a metal nozzle, it would just, not just melt, it would simply evaporate, to be honest. So what do? You use some kind of magnets, not just any magnets, but you try to use superconducting ones if possible. And we also have superconducting magnets. So we have superconducting magnets to ultimately create an invisible force field that shapes the plasma and pushes it out the back, basically creating this exhaust. That, of course, creates forward thrust. One important detail here, yes, I think that's included in the text. Let me check really quickly. Thank you very much. I can't find it now, but it's definitely in this text. This VASIMR emits a quasi-neutral plasma. So quasi-neutral basically just means ions and electrons at the same time. With other ion drives, you have to be a bit careful that the spacecraft doesn't somehow become statically charged and basically fry itself with a lightning bolt. For that, you would need a neutralizer, and you don't need that with this drive. So it's a very elegant solution in the end. And what I wanted to get back to here, which I thought was a really cool analogy, is when all of this started back in the 1980s. Back then, it was also classic, well, science fiction. Mm-hmm. Just like we've mentioned a few times now, ultimately. Yeah, let me put it this way. Rome wasn't built in a day either. And so now this lower half, more or less, of this page, it basically shows a lineage of this whole project. And this isn't just some random idea from yesterday. You can see that right away. They've been working on this for, you have to think about it, for almost 50 years now, more or less. Definitely for over 50 years. The foundations were built at MIT, which is why it was launched there too. In the 1990s, things continued at NASA. That's when the first larger tests were conducted. And from, well, here it says 2000, but let me add, from 2005 to be more precise, the whole thing was privatized, namely in the Ad Astra rocket company, in order to finally be able to build a market-ready engine for it, also using investor money. So really, yeah, a totally cool thing. And this paper isn't actually that big. I don't think that's so bad. Because if we move on here, let me just check real quick. We can actually skip this. We're about to get to that anyway, a bit more in detail. Here we see such a nice can, you could almost say. I'll zoom in a bit more. Exactly, now you can see something that works. Really cool piece. You can also see how big such a vacuum facility actually is. In the photo, you can see a gigantic steel tube in the middle, and that's a vacuum chamber. The problem is, as we mentioned earlier, the engine shoots a massive amount of gas, the argon, and incredible heat into this chamber. So it's kind of like turning a heater on full blast inside a tiny sealed tent. And after 2 minutes, the air, or in this case, the vacuum, is completely ruined and everything just starts melting away. And of course, a solution was built or ultimately designed for that. We can see it here. You can see it a bit better here. Let's scroll down a little. Exactly. This is essentially the solution. You can also see the size and the engine inside on the left again. Here, so this purple plume, that's ultimately the plasma that comes out. That goes directly into special graphite curtains. Those are these gray foil baffles. It should be written somewhere. Here, gray foil baffles. Those are these graphite curtains. You can imagine it like a gigantic fireproof catcher's mitt, so to speak, that absorbs the heat and then transfers it outward into the cooling water. Totally brilliant thing. That way you can test something like this in the vacuum chamber without the whole vacuum chamber getting ruined. And these tests are also crucially important, for example, to be able to prepare or actually determine a technology readiness level. But what's important here, of course, is that we somehow have to keep a diary. In engineering terms, you have to keep a diary somewhere to collect our pains. So a pain diary, that actually sounds pretty good. Of course, that was done as well, and we can see that here in this figure. I'll zoom in a bit more. Oh, a bit too close. Yeah, about like that. We definitely see a graph here. That's pretty cool. And this graph is, I would say, pure science, because it actually shows that it's rare for something to work out the first time. We see here on the x-axis, so horizontally between mid-2018 and early 2019, so roughly from June 2018 to March 2019, you can see there they tried to run the engine at high power for just half an hour. So here we have total output power on the y-axis. What else can you see? From the labels between the bars here, without having to crane your neck, I'll just quickly explain to you how they constantly had to stop it, or why you had to stop it. First, the seals were broken. My dog is freaking out. Hope the background isn't too loud. On the one hand, the seals broke. That's something that's always a problem. Then, of course, we also have the issue that the cooling isn't enough because of the brutal heat. So that's why there was a second campaign and eventually a third and fourth campaign. And the front panels have to be redesigned. So it's a constant process of trying something out. It doesn't work. You have to tinker with it again and set it up from scratch. That's always how it goes in the end. And then finally, the breakthrough came. And you can see that here in this red box on the right side. The red box on the far right is campaign 5. It's simply another campaign, but in red, that's the breakthrough. That's where it basically clicked. So on the one hand, they had solved the heat problem, and at the same time, you can see the performance curve, which shot up to those 80 kilowatt. We actually reached 83, so to speak, exactly. Yes, exactly, 83. And that's how it was. That's necessary hard training, which ultimately made this 88-hour record possible in the first place, which we briefly talked about earlier. So in short, Ad Astra in this case not only had to invent a revolutionary engine, but also had to build this high-tech tube that we saw up here that can actually withstand it, so that you don't completely fry everything. So it's a really fascinating topic in the field of plasma physics, or more precisely, applied plasma physics within an engineering field, namely aerospace engineering. There are also some other cool pictures, since people always like to see them. So where are we? No, I didn't mean those. It's not that important. Here we are exactly. Here we are. Now it's actually about these TRL5 tests and the PPU. So PPU is the power processing unit, by the way. So basically the power supply, more or less. And without this thing, even the best plasma thruster is useless. So just imagine the PPU really like the bulky power supply of your laptop or something, except you need it for an entire spaceship, basically. That's one way to think about it. And here in the middle, we see a shiny cylinder. That's the new PPU, the second generation. Of course, it has a specific task. It consumes, let's say, the regular direct current from the spacecraft, for example, from huge solar panels. That's always direct current that's generated there. And then it converts it into the high-frequency radio waves, which are emitted at 500 kilohertz, by the way, which the engine needs to basically grill the plasma. Totally brilliant. A lot of power is generated there too. What are the 500 kilohertz and where did it mention power? Ah, there, 120. Really brilliant. So this thing has 120 kilowatts. That's really a lot. It's like charging an electric car at a supercharger. So that's quite a lot. And it also has an insanely high efficiency of 98.3%. That's crazy. We have losses here of just over 1%, not even 2%. But of course, we still ultimately have the vacuum problem. In the past, electronics used to just stand around comfortably in the lab, out in the open air or so, and not much happened. That was TRL3, TRL4. So everything that's in the lab environment only goes up to TRL4 at most. And now they've just screwed the thing directly into this vacuum chamber. That means we can also make TRL5 out of it because it appears together in combination. You have to know one thing about electronics. They hate vacuum. No matter what kind of electronics, all electronics hate vacuum. Really? Because there's no air to carry away the heat. I think we've talked about this before. Exactly. So about cooling, that's why you also need radiators and such. The rest, so we had one here, I already mentioned that. We had 98.3 here. Yes, 1.7 are missing. So these remaining 1.7% of power loss are still over 2,000 watts of heat that can't go anywhere in a vacuum. So that's quite a bit that just can't go away here. That's annoying. That's why they said, okay, maybe we need to build some kind of dummy test or something like that here. First, we'll discuss this picture, then go down again. So how do you test a mega power supply without accidentally blowing up the whole lab? Well, of course, you just connect a dummy load to it. Yeah, that's logical. Well, not really, but whatever. Here you can see again in the middle, well, actually not in the middle, but at the bottom right, this PPU, the one we just saw in the close-up, we can see that there's a 50 ohm step-up network connected to it. Here are these RF lines and the DC lines, meaning DC direct current. And at the bottom left, we have a dummy load in a blue box, basically. So you can see here how the current, that's the blue line, goes in, and the radio frequency or the RF frequency, that's the green line, to one then goes on here to a cool, meaning a water-cooled resistor, that's the dummy load, where it's dissipated. That means the engine didn't really run here at all, so you have to imagine it like this. The engine didn't really start up here, so it actually didn't run at all. They only let the PPU, the power processing unit, sweat it out in a dry run here, so to speak. And these colorful hoses, the vital cooling systems, this was only about the electronics. This way you can ultimately test the electronics separately, even though they're connected within the whole concept, within this entire system. Actually, a cool thing, we still have a problem, so I'll go one level deeper. So let's take a look at this here. A few lines and other things remain here. Yeah, looks like an EKG. It is, in a way. It's kind of like the EKG of a power supply. This graph, which looks a bit complicated, basically says just one thing. The test has been passed. That's pretty cool. They turned the power supply to full, and it ran steadily for 4 hours. That's clear from this. I'm referring to the straight lines at the top of the graph. Then, of course, there was the ultimate stress test. That happened, wait a second, 3:30 p.m., 3:30 p.m. in the graph. That's when they turned on the huge superconducting magnets of the engine next to it. At least that's what the text says. That means you have strong magnetic fields, which usually make normal electronics go crazy right away. But the PPU, thanks to its shielding, didn't even bat an eye, so it worked really well. You have this awesome power supply here, which actually worked to power this plasma drive. That's really brilliant. And now we're slowly coming to the end here. Let's scroll down again. Let me double check. Yes, these are correct. Let's review both targets, but not simultaneously. Yes, a little bit more there. These two graphs, that's really the triumph over this, what did I call it, sweaty lab. Let's take a look at the first two graphs. So mainly, yes, exactly, the first ones. Let's see exactly the first two graphs. Let's look at the lowest jagged blue line. Here, the 6x, that's the lab's cooling water temperature. It keeps getting warmer, then slightly colder again. But there's actually a bit of magic behind it, because if we look at the lines above, those are the temperatures in the drive system, the green, orange, and light blue ones. We can see something. That's important. They are almost not perfectly straight, but almost perfectly straight. After about 30 minutes, yes, exactly, 30 minutes, the system reaches a kind of thermal equilibrium. So here we have 3:20 p.m., it goes up a bit here, and then about half an hour later, we have this steady state that we wanted at the beginning. What does that mean now? Well, the cooling water of the drive is so incredibly good that it really doesn't matter at all whether the lab cooling water is fluctuating or not. In the end, the engine just stays cool. Of course, I mean the drive's cooling system. That's obviously a great thing. And we can see the whole thing confirmed down here again, just in a different time frame, but of course, there's always a but. Let's take another look at this here. We have two more graphs, two tables. Yeah, what should I call this now? A direct look, a straight look into hell. Why? In the summer, it must have been in the summer, it said so somewhere there. Campaign in the summer 2021, yes. Exactly, in the summer of 2021, there they are again. They have infrared thermometers, those are pyrometers, installed, which look directly at the components, so at the ones where this 1,000,000-degree hot plasma shoots past. And especially in the upper one, so let's take a look at the upper one, that's Fig 13, that's a 10.5-hour test. It ran, so it looks good. We see here again, okay, very nice lines. Absolutely smooth. That fits as well. Surface temperature, that's the one on the right. We have two y-axes here, left and right. The right y-axis, usually around 400 degrees, sometimes up to 700 degrees, settles somewhere in there, but stays stoically on one line. Very cool. Now let's go down again and take a look at that. Oops, down here. I'm going to zoom in a bit here again, so that we still have everything in view. There we go. Let's take another look at this. This is a 28-hour test marathon. What do we see here? Well, this thing ran continuously for the whole day at over 80 kilodau, and the lines are flat as a board. Nothing melts, nothing overheats. And that's even though we sometimes reach 800 degrees. So here and up here, we're also at 800 degrees. I'm not even sure. Well, no, not quite, 700. So we're basically looking here with the devil's eyes, so to speak, directly at the materials that the plasma shoots past, and we see that everything remains stable. Very cool. But there's one thing we shouldn't forget, because we've talked about it so many times in this podcast, and it's probably going to follow us for a long time and always be a miserable topic. Space travel will always encounter bureaucracy. And that's probably the funniest detail in this whole, or rather in this whole rigorous scientific paper. I think that was up here above this figure 13, what's in the text. Yeah, I'll just leave it open like that so you can kind of follow along a bit. Why? Or I'll just ask now, can you imagine, Simon, why they stopped the 28-hour test exactly at midnight on June 30th? Any idea? Wild guesses. It says here.
What?
Why could that have been?
It says so right there. The contract officially ended, and that's why. Yes.
That's just, it's always the same.
Because the contract officially ended, they didn't think, okay, we're in the middle of the test, let's at least finish the last 2 hours, right?
Yeah, so to speak. Well, you could first say or speculate, well, maybe the drive broke down or the argon ran out or something like that. Nope. But rather because exactly at midnight, the NASA contract called Next Steps officially expired. So what can I say? The engineers basically pulled the plug and called it a day.
Are they maybe Germans or Austrians?
or something like that. No, it's the same in the US. I mean, if you don't get paid for it anymore, then just shut it down. I think it's actually even stricter there in some ways, at least in that regard. If there's no contract, then nothing gets done at all.
I think that if you're a researcher or an experimental physicist or something like that, and you're right in the middle of doing something, the resources are already there, everything is already running, then to say, well, okay.
You tell the managers, I think the engineers and the scientists would have had a great time there. But yeah, if you talk to a project manager, they'll tell you something completely different, but that's the same everywhere. So unfortunately, that's really the case everywhere, but it really is.
Crazy. Yeah, crazy. I mean, to be fair, I can also imagine that it has to do with safety and insurance. And if something should happen and you're contractually protected, that problems can arise. I get that, but still it's kind of an absurd bureaucratic thing that happened here. Funny?
Also completely unnecessary, really, when you consider the reasons why. So on the other hand, we still got the proof here, thank God. Maybe timing-wise, it was a bit unfortunate that it ended up being pushed so far back, but we have proof that it works, and we have proof that bureaucracy can throw a wrench in your plans within these figures if you didn't want to interpret it that way. But what's also super important now for this whole topic, why did I bring up this topic of plasma drives? I mean, we already have chemical drives, we have ion drives, we have this and that, there's talk about nuclear drives and so on. But to understand why Vasimar can now shrink the travel time to Mars, for example, from typically 7 to 9 months down to an incredible 39 to 40 days, of course, we also have to look at how we currently travel through space. And that's where a Vasimar engine is really a great thing. I also have something else open here at the same time, so let me quickly check if it's there somewhere. Tram. Yeah, we could actually just quickly go over that. I'll just quickly share this page as well, just a second. Come on now. So you should actually be able to see it. I've already clicked on share.
Now it's coming, yeah.
Okay. Looks good, right? Yeah, same here. Exactly. I'll just scroll through it quickly so we have a bit of context. As you can see, it's now about mathematical methods. And here it's about the estimation of erosion phenomena within helicon plasma sources through a steady state explicit analytical model. In short, we've reached plasma kitchen stage 1. I'll head down here again quickly. And of course, this is again about our Vasimar drive. I'll go in again. I hope you can see everything. Also in the right size. Looks good. Exactly. This illustration here, I mean, this really big thing in general, and I especially mean illustration A. So this upper part, you can see the plasma pod again there. So on the left, the cold gas comes in from the propellant tank, these little squares. At the top and bottom are the magnetic coils, which create the invisible magnetic tube. And then you also have this RF generator, this generator in the middle. That's a highly developed microwave again. So we've already understood how it works. If we look at it below, I'll make it a bit bigger again. What's written on the right doesn't matter. This way you can see it better. Exactly. Plasma is ultimately, and you have to remember this, it's like a bunch of extremely hyperactive, unbelievably annoying charged teenagers. That's plasma. That's how it is in the field of particle physics or generally in the field of physics. No, it's really like that, really. Controlling that stuff is just difficult with them. It's sometimes really unpleasant and heats up fast. Stupid, just stupid. Wants to go everywhere and breaks things. And that's exactly what this picture shows. This picture shows the wear. So ultimately the erosion, because between the plasma and the wall, that's the electric boundary, so to speak, an electric potential field builds up. That's, so to speak, does it say that anywhere? I'm not even sure, but it's a plasma shelf. It's probably here, there it is, plasma sheath, that's the name, not shelf, exactly. What's happening there? The ions are being accelerated against the wall like tiny cannonballs, so to speak. So atom by atom, they're slowly knocking the material out. That's this, I'll call it the evaporation effect. It's really annoying. That's also the main reason why such engines break down in the first place. You have to design this extreme magnetic field in such a smart way to keep the plasma away from the walls. That's super important. And a big problem, unlike with chemical rockets and so on, has always been the math. That looks here, well, it's actually not that bad. We just have a few little formulas here in the end. But in a way, it's kind of a termite problem in the end if we take a look at the whole thing here. It's kind of a jumble of formulas, but I just want to quickly go over these formulas here. So mainly, I'll try to zoom in a bit. Let's start, oh, that was too far to the left. Let's start with this one here. Yes, exactly. These equations 1 to 3 look super complicated, but basically they're not. Actually, you can show both of them now, all three at once, then you'll immediately know what I'm getting at. All of this here, especially equation 1, equation 2, and equation 3, that is left, top right, and bottom right. That's basically the recipe for all the engineers. What do I mean by that? It basically and quite strongly says that the thickness of this plasma soup, in other words, the plasma density N0, is what it ultimately comes down to. That directly depends on how strong the magnets are in general. So if you want more thrust for your spaceship, you just need stronger magnetic fields. Broken down really simply. This side ultimately shows how to turn gas into plasma extremely efficiently. That's the helicon principle. But of course, you also have to be extremely careful that this plasma doesn't literally tear the pipes apart. Yes, or rather scratches them. So much for that. If you want, of course, we can also go into the formulas themselves, but I don't want to bore everyone to death here. But yes, that's why it's important that we look at plasma drives and above all, that we approach this scientifically in depth because we simply need alternatives. So we can't always limit ourselves to the classic chemical drives that we know and have. I mean, SpaceX quickly went ahead and said, okay, let's take a look at methane. That was really unusual at first, even though it had already been tested in the 70s and 80s. It was tossed back and forth again and again. But ultimately, looking at a new propulsion system that actually makes sense, especially in terms of acceleration, definitely makes sense. Personally, I believe that plasma drives have a great future. If we can do a bit more research on materials, if we manage to control the temperatures, then nothing really stands in the way anymore. And then we actually have drives like the ones we know from, I don't know, Interstellar, Star Trek, Star Wars, or whatever comes to your mind. Those are plasma drives. The cool thing is you have a gas tank, you heat it up, and then you send out this plasma. So basically the heated gas that shoots through here passes through a generator, blah, blah, and thrust comes out the back. You can turn magnets on and off quickly. That means you get thrust or braking effects super fast. Theoretically, you can add those reverse things like on an F-22 and get reverse thrust. Who knows where it will lead, but yeah.
That's cool. That's almost like hypergolic fuels that you can really use for landing and navigation. So for precise maneuvers.
Yeah, good comparison, exactly. It's going in that direction. It's going in that direction. Very exciting.
Exciting. I've already talked a few times about future propulsion systems that could reduce the transit time to Mars to just over a month. Incredible. That's crazy what might be waiting for us there. And that's why I always find it a bit sad when people label things as science fiction and say, not that, that's not possible, we don't want that, we don't know that, it didn't work. But we see that even science fiction concepts definitely have a place in research. Yes.
We also need this idea, this free thought in our minds to be able to dream. So everything we see somewhere, everything we hear somewhere, anything we notice, anything new and great that comes onto the market and so on. We often discuss SpaceX, but there's also much happening on a small scale in this area. And by small, I mean visually and materially small, for example, in microelectronics or the like, or maybe also in the field of quantum. If you don't, I'll just say it bluntly, if you don't dream of some cool vision, which is always science fiction at first, then you won't get the chance to do research in the right direction. There's also something else I find cool. It's totally different, and we can discuss that too. There's a concept of how to send information via microwaves, for example, from the moon to the Earth. Something like microwave transport, microwave power transmission. And with information, I don't just create data, but even pure energy. So simply put, you basically harvest an incredible amount of energy on a huge solar farm on the moon and send it down to Earth with a microwave beam over this vast distance, nearly 400,000 kilometers. And it does arrive, it definitely arrives, even with losses, enough still gets through. And you can actually capture it and then feed it into the grid through many generators and the like. That's the idea. It actually happens in a few video games as an alternative energy source. Really brilliant. If you say now we don't want to go that far away toward the moon and maybe not put it in a LEO, but maybe in MEO where there's still a lot of space, or you're far enough away in case it breaks, where you can deploy large solar arrays without immediately having a Kessler syndrome if a meteorite or some small meteorite hits and damages them. And you can keep developing this technology so that you can still beam the energy down to Earth, no matter who does it. So theoretically, actually more towards geo, now that I think about it. But yeah, whatever. We have to dream, otherwise nothing will happen.
First of all, if you don't dream, then someone else will dream for you. And if you...
Right.
And what you just described, this concept, that's not even science fiction anymore. That's actually a concrete project by ESA, for example, Solaris. ESA is working on it.
Yes, it was. Yes, exactly. That's right. That's a fact.
And JAXA, the Japanese Space Agency, is also already working on it. They already have some very concrete examples. They have already beamed energy back from space in a very concrete way. So there are already pilot programs that...
But there we have the problem with the TRL again. That's exactly it. So you have a technology readiness level that settles somewhere between 1 and 3. Yeah, unfortunately still.
Not that far yet, yeah. But it's definitely not absurd now, not just somehow conjured up from some book, but it's actually somehow based in reality. Super exciting. So we've just gone a little over 2 hours now. Is there still a major point missing, or have you already? No.
But from my side, we've now covered everything roughly that fits. Of course, you can always go deeper, but considering the time, I think everyone will be satisfied with this.
Yeah, totally. Well, great. Then today we've once again covered a wide range, covered the most important news, and brought in another super cool science topic, science, technologies, engineering topic at the end. Thanks for that, Alessandro.
You're very welcome.
It's a lot of fun. I always learn a lot with you, and I think the audience really enjoys it too. It's a shame we do this so rarely, but maybe that's what makes it special, right? Which makes the anticipation even stronger. I'll make sure to get this video ready for editing and upload it quickly, so it might even go up today or at the latest tomorrow. So I want to thank you again very much. Thank you for your time, for taking the time today so we could do this together. Thank you as well
for being such a great host here. I have to say, it always works out wonderfully. I also think the channel keeps developing nicely. That's why it's definitely a great thing. Cool that I was able to be a part of it.
My pleasure. Always super exciting and educational. But of course, a huge thank you to you all for sticking with us until the end today. If you've made it this far, feel free to check out Alessandro's channel, Alessandro Rosner, just like it says under his face. Subscribe to his channel and check out his videos. Really cool stuff about technology. Also, feel free to subscribe to this channel. Consider supporting us as channel members. Here on Mars Chronican, you always get the videos early. Before they go public, as soon as they're edited, they're made available to channel members. And on our own behalf, the two of us also run the Planet Pioneer shop together. Alessandro runs it, but it's actually also my Mars Chronicles shop at the same time. So feel free to check it out, support us, and get our cool designs.
I'm not wearing merch today. Scheibenkleid is here, but I just came from work. That's my excuse.
And you can also see some teasers behind me of what's coming up for you. For the upcoming launches like Starship and SLS, we will now start offering rocket models in the shop, at least in limited editions, really strictly limited. We might also offer the Falcon 9. We still have to see if that will be limited and how limited it will be. But it will definitely be available in the shop soon. So feel free to check it out. Exactly.
We still have to wait a little bit, but there will be some really cool limited stuff coming out. I should also mention it's all handmade. So it's not like we're buying in bulk from some big company and then just selling it to you at a high price. No, these are really pieces that were handmade with love, from the code to the printing. That's a fact.
Yes, indeed. That was quite a lot of work to coordinate everything, getting the licenses, sorting out the licenses, clarifying everything with the sponsor to make sure everything is legally correct, that we have the right licenses. But now everything is settled. All the contracts are signed. Production is now slowly getting underway. And it's more work than I thought it would be. But that's that for now. And now, one last remark. If you're watching this video, please give it a hype right away, because this hype only works for the latest upload. That means when I upload something new, you won't be able to hype this video anymore. So feel free to hype it right away when you see the video. And if that's no longer possible, just give it a thumbs up. Subscribe to the channel. That already helps a lot. And of course, the same goes for Alessandro and his channel. Feel free to check it out. Take a look around his channel. It's a lot of fun. He does a great job.
Feel free to stop by. Thanks for the shameless promotion.
Definitely. At least we limited it to the last 2 minutes. And we didn't make it too heavy of an advertisement.
The core audience is still here.
Exactly. In fact, 25% of the people are still here after 2 hours. That's impressive.
Hey, hats off to you. Awesome.
Yeah, super exciting. I get that too. That's a cool show. So let's check it out. All right. So once again, a huge thank you to you all. Have a nice day. Once again, thank you, Alessandro. See you soon. Per aspera ad astra.
Take care. Bye-bye.